Right, recording is rolling. It is Friday, March 31st. So we're gonna finish this page today, and I'll have you guys turn this in by the end of class. You just follow along with me, and you're gonna be all right. And then next week I have some Kahoots with some conceptual questions lined up. I have a few more labs. You have you guys. I want to have you guys figure out what's the resistivity of Play-Doh at some point. Have you guys construct a motor and an electromagnet. So that's going to be next week. You guys know next week is a 4-day week, and then we have a Good Friday off. Okay, so let's warm up with some circuits on the side. We'll just do a couple circuits here. We're going to do number 8. And so number 8. Okay. So what is the equivalent resistance of this? Okay. So you remember we find our voltage source, which is right here. We're going to fly over to the opposite side of the circuit and work our way back towards the voltage source and find equivalent resistances all along the way. So first are these two, R2 and R4. Guys, R2 and R4, is that parallel or series? How many of you think parallel? Parallel. Yeah, I also think parallel, because whatever current makes it to this part, all the current at some point is going to make it to this junction. Then the current has to split and be pushed through both simultaneously. So we're going to treat that as a parallel setup. Parallel. Okay, so let's do resistance equivalent is R2 times R4 over R2 plus R4, right? Product over sum. Okay. So that's 8 times 5 over 8 plus 5. Of course, my numbers are different than your numbers, but it's the same process, right? So these two guys in parallel, product over sum. You guys just did that? So that looks like 40 over 13. That comes out to, get a decimal. Okay. How many ohms is that? Okay. No, that's not the final answer. That's just a middle step. Okay. Then you need to redraw the circuit. Redraw the circuit. Voltage is still there. R3 we haven't touched yet. That many ohms on my paper. R1 we haven't touched yet. That's that many ohms on my paper. And then R1 and R2 and R4 collectively make one resistor. Bam. Right? It's as if there's a single resistor there. Okay, all good so far? Okay. Remember, one of the analogies I've been using is resistors in parallels, like guys teaming up to do a job, for example, painting a fence. So if it takes one guy 8 hours to paint a fence, the other guy 5 hours, if they team up, make a 2-man team, they can knock out the job in a little over 3 hours. Okay, also makes sense. Okay. Remember, all this electricity stuff also has other applications. So you can do, like if you have a big project, and sometimes you need steps to be done sequentially, and sometimes steps are done in conjunction, like in parallel with each other. Okay. You can do like a time management project, and the math works exactly the same as circuits. You could do traffic flow if you're a traffic engineer. You're trying to. You could do. You could design a pipe system for a whole city. Like a lot of things in physics for this entire year. Like whatever you're learning for some specific thing. Like right now we're doing circuits and electricity. Okay? It always you can take these models and apply it to other things in the world. Okay? And so next step, these 3 resistors now are all in what with each other? Series. So can I just add those 3 up? Add them up. Okay. So that's 9 plus 3 plus 7. So resistance total is this many ohms. That should be an answer choice on your paper. Boom, right there, right there. Okay. Are we good? All right, let's do one more circuit from the side. So there's a pair of questions down here. You guys see 13, 14 down here, 13, 14? Okay. This will be the last one we do from this side. So here's my voltage source, fly over to the opposite side. That looks like R3, okay, R3. Ooh, and that is in what with R2 and R4? R2, R3, R4, those are all in what with each other? Series. Yeah, so you can just add those up. Add up R2, R3, and R4. So R2, R3, and R4. So 4, 5, and 2 ohms. 4, 5, 2 ohms, ohms, ohms. That's that many ohms. Okay. And then redraw your circuit. Okay, R5 we haven't touched yet. So for me, it's that many ohms. Oh, hold on. Or 2 or 3 or 4. Oops. Touch it. That many ohms. Okay. R1 we haven't touched yet. That's that many ohms. R6 we haven't touched yet. So for me, that's that many ohms. And then R2, R3, and R4 collectively, it's as if there's a single resistor there. That's the one we just calculated. So you guys redrew your circuit. It looks something like that. Okay. So it should be the same geometry, just different resistance values. Okay. So again, we're working back towards the voltage source. We're going to run into, bam, that guy right there, which is R6. Okay. So these two guys now are in what with each other? Parallel. Okay. Because the current at this point hits this junction, it has to split. The current has to split, okay, and be pushed through both simultaneously. That is parallel. So let's do product over sum. Okay. So resistance equivalent for that part of the circuit is this product over this sum. 33 over 14. It's like 2. Then redraw your circuit again. Right. And those three now are all in what with each other? Series. Aha. So the resistance total is, just add them up, 7, 8, 9, 10. Looks like 10.36. Just add them up. Add them up. There should be an answer choice on your paper. Boom, right there. An answer choice. Okay. So recap that one while you guys are wrapping that up. First thing we did was we said our 2, 3, and 4 are in series, so you just add them up and write that down. Then redraw your circuit, looks like this. Then you bring in R6, and that's a parallel relationship, so you do product over sum. Redraw your circuit again, somewhere, bam, right there. Okay. And then the last step is whatever's left over is all in series, so you very simply add them together. So it's as if there's a single resistor for that entire circuit set. Now the follow-up question is, what's the current? I told you guys 5 volts, just like your lab yesterday, you working with those 5-volt chargers. So let's switch over to Ohm's law. Ohm's law, the current that flows is the voltage acting on the resistance. So we've got 5 volts being pushed through, and a resistance of whatever your answer to the previous question was, this many ohms. That'll tell you how many amps of current are going through the battery. So that's the total current supplied. Bam. Okay. Of course, that current is going to hit this junction and then split and then come back together with this junction and then go back through the battery. Okay, that's the total current. Ohm's law. Okay, everybody good there? Good there? Okay. All right, so these two circuits we're going to skip, but you should have everything except for these two at the bottom. Okay, everything except for these two. You guys got this? All right. We're going to take the rest of the class to do these last 2 waterfall models, and then I'll have you guys turn this in, and that will be a wrap on the week. Okay. So let's do number 3 first, because number 3 is a little bit easier than number 2. Okay, so number 3. Okay. I'm going to break out my colors, see what's going on in terms of voltage plane. So I'm going to get pumped up to so many volts. Now, I have a 12-volt battery. Do you guys see how many volts your battery is? How many volts? So it looks like right away, the current is going to split. It's going to split 2 ways. Part of the current is going to go all the way down across resistor D to the valley, across resistor D. So resistor D is going to represent a really tall waterfall. Then the current that doesn't go that way is going to go across resistor C. So there's a single waterfall there. And then hit resistor B. And we got another waterfall right here. And then that's going to go combine with the current that went through resistor D, combine together, go back to through the battery. So we look like this. So this current's going to split right here. We have a big old waterfall right here. A splash. Big tall waterfall. Then this current goes back to the battery. Meanwhile, up here, this pink current split, a splash to this yellow plane right there. Then it dropped again, a splash to this orange plane. Then finally it dropped again, a splash to this green plane. Right, just like that. Right. All good? All right, so we got some numbers here. I told you how many volts the battery is, and I told you how many ohms each of the resistors is. Okay. So let's figure out what is the equivalent resistance for the entire circuit. Oh, well, that's what we've been doing as warm-up today. Okay. So here's my voltage source, fly over to the opposite side. I'm looking at resistors A, B, and C. Now, A, B, and C are all in what with each other? Series. Okay. So whatever current goes along that branch, you can see it with waterfall model too. It's just the same current. Dump, dump, dump. Better be the same current in amps, right? So we can add those together. A, B, and C. Now that's these three boxes. So for me, that's 3 ohms, 2 ohms, 1 ohm, 3, 2, and 1. So that's going to be 6 ohms. So resistance equivalent is 3 plus 2 plus 1 ohms, which is 6 ohms. Right. Then redraw the circuit. Voltage. Right. Now resistor D we haven't touched yet. So he's still here. Right. But A, B, and C, collectively, it's this many ohms. Right. You guys did that? Right. Now, if this is your whole circuit, then these two guys are in what with each other? Parallel. So the total resistance, oh shit, I should do product over sum. Okay. If there's 3 hours of paint fence and 6 hours of paint fence, they team up, make a 2-man team. Yeah, I think maybe 2 hours they can knock it up. I think so. What's 3 times 6 over 3 plus 6? That is 1899. Yep. That is, in fact, 2 ohms. Right? So that's for the entire circuit. It's as if all these guys together are acting as one giant 2 ohm resistor. Okay. I think I mentioned too, all the numbers on this paper with waterfall models, I try to make come out to nice numbers. So you might have whole numbers. Like I only have whole numbers. I don't have any decimals at all. If you do have decimals, it might have like 1.5 or 2.5 or something like that. But you won't get anything crazy. So if you get something like 2.2367, okay, then something messed up somewhere. Okay. Are you guys getting nice numbers? Yeah. Next step, voltage drops. Ooh, well, there's one that stands out right away. I don't even need calculations for, and that's the voltage drop across D. Okay. Guys, what is the voltage drop across D? It's the same as the battery, isn't it? Okay. And that is consistent with the loop rule. Like my battery's pumping up 12 volts, and this waterfall goes down all 12 volts. Up 12, down 12, up 12, down 12. Resistor D has to match your battery. Right? Battery voltage. Okay. You guys got that? Just copy paste that number. Okay. But resistors A, B, and C, it looks like it's going to fall down a little bit, a little bit, a little bit. I mean, these three waterfalls better add up to 12 volts total height, right? 12, right? But it's a little bit at a time. Okay, now here's where we need to break out these Kirchhoff rules. Actually, I'm going to go back and rename this like Kirchhoff rules and friends, because or Kirchhoff rules. There's really only two rules, which is this loop rule, which I'm also going to not make strictly serious, but I'm going to redesign this poster. What I'm saying, right? And the junction rule, right? But these are all the rules that follow out of this. I'm specifically looking at this one right here. The voltage drop. So as long as you're on a series part of the circuit, and we are on a series part, there's A, B, and C. The voltage drop across each one is proportional to that particular resistor, right? Something like that. Now we have 3 resistors instead of 2. There's one difference, but that'd be all right. So I'll start up here at C. So here comes the current around across C. So the voltage drop across resistor C is whatever resistor C is over resistors A plus B plus C. Okay, so it's like a ratio. Okay, all times the voltage drop from this junction to this junction, which is the same as the voltage across the battery. Okay, right, so that'll work for everybody. So plug in my numbers now. My resistor C is 3 ohms. A, B, and C is 3, 2, 1. And then my battery, or from this junction to this junction, which is the same thing, is this many volts. So that's 3 out of 6 times 12 volts. Half of 12 volts is 6 volts. So across resistor C, I have a 6-volt drop. That's half the total voltage, because 3 ohms is half the total resistance on that branch in the circuit. 3 plus 2 plus 1. Okay. Yeah, checks out. Right, we can do the same thing for resistor B and resistor A. So the voltage drop across B, well, resistor B itself is this many ohms. It's the same branch, so it's the same 6 ohms total. Okay, and same junction, we're looking at 12-volt drop. So a third of 12 is like 4 volts. That's bam right there. And resistor A, what's the voltage drop across A? Resistor A is this many ohms. The whole branch is this many ohms. This many volts. This many volts. Bam. Just like that. All right. Working out. Okay, now, if you did it right, then if you look at C, B, and A, these 3 voltage drops should add up to the voltage drop of the battery. Okay? Like for me, this is 6 units, 6 volts. This is 4 volts, and this is 2 volts. 6 plus 4 plus 2 is 12. Okay. Do these 3 boxes add up to your total voltage? Okay. Guys good? Okay, guys ready for your next step? So the next column is current in amps. Now we're ready for Ohm's law. The current that flows is the voltage acting on the resistance. So this V divided by this R. You can really just divide these 2 cells. Zoom in here. So V over R. 12 volts on 3 ohms, that's like 4 amps. 6 volts on 3 ohms, that's like 2 amps. 4 volts on 2 ohms is 2 amps. 2 volts on 1 ohm is 2 amps. Okay. Now, regardless of the specific numbers I gave you, whatever battery you have, whatever resistances you have, these 3 boxes have to be the same number. Not necessarily 2. I have 2 amps. Okay? But however many amps you have in this box have to be the same as here and here. Because see how this is like one continuous stream? Like if this is 2 gallons per minute, this is 2 gallons per minute, and this is 2 gallons per minute. Okay, do you have the same number of amps for all these 3 boxes? Okay. Okay, how about the current through the battery? Two ways you can do it. You could say, here I have 4 amps coming down this waterfall. So maybe I should make a really fat waterfall right here because this is 4 amps versus this is only 2 amps, right? This waterfall is twice as wide as each of these. I've got 4 amps coming down the stream. I've got 2 amps coming down the stream. Guys, what's this 4 plus this 2? That'd be 6, right? It should be 6. Or you could just apply Ohm's law at the point of the battery. 12 volts supplying across a 2 ohms total. That's also 6 amps, isn't it? It's 6 either way. Of course, your numbers are different, but the same principle should apply. This 4 plus this 2 is 6. This 12 divided by this 2 is also 6. Are we good? All right, last column, power and watts. Let's switch over to Joule's law. Power is current times voltage. Or if you like, you do current squared times resistance or voltage squared divided by resistance. They'll tell you the same thing. I'll just do I times V, current times voltage. 4 amps times 12 volts, that's 48 watts. 2 amps times 6 volts is 12 watts. 2 amps times 4 volts is 8 watts. 2 amps times 2 volts is 4 watts. Okay. Oh, I forgot to type this step. It says circle the brightest bulb in the circuit. Okay. Wouldn't power and watts tell you the brightest bulb? So which one's my brightest bulb? Resistor D, because it's like 48 watts. Okay. That's probably also true for you. Your brightest bulb is probably resistor D. Okay. It's 48 watts. It's gone. Right? All right. Finish off this table. I've been telling you guys 2 perspectives for this last cell, and they should agree on each other. So if you did this entire table correctly, these 2 perspectives should agree. Okay? You could just apply Joule's law at the point of the battery. You say I have 6 amps, 12 volts, 6 times 12, that's 72 watts. Okay. Alternatively, you can say, does electricity supply match electricity demand? So each of these bulbs is demanding some amount of power. Let's add those up. What is 48 plus 12 plus 8 plus 4? Okay. How many watts are being demanded? Oh, 72. So there better be 72 watts also supplied by the battery. And it's a match. Okay. You guys good? Are we good? Who's got any question on that circuit? Any question? Right, so we got 1 waterfall model left. Okay. And ooh, this one's going to be the challenge. Okay. So let's get some voltage planes going. So my battery is going to pump up 12 volts again, just a 12 volt battery. Okay. This current is immediately going to split. So part of the current goes this way, part of it splits off this way. Okay. Whatever goes through resistor E is going to drop all the way down to the valley because that is connected to the negative lead of the battery. So connect like this. Okay. I bet we're also going to get a stream somewhere from like over here eventually. It's going to come back together. Great. Let's go. Yeah. Oh, it's a yellow plane right here. Right. Oh, so whatever current ends up going, so here's resistor E. Resistor E, I have a tall waterfall, same height as the battery, same voltage drop. And then whatever doesn't go through resistor E is going to split off and go through resistor D. Okay? And that is going to split off across A and B. So I need the current to split right here. Bam. Okay? I'll have side-by-side waterfalls. Here's resistor B, here's resistor A. A and B side by side. Then that current is going to come back together. And final waterfall is resistor C. A splash right there. So you guys okay with the waterfall? What's it gonna look like? Right, so I told you the voltage from the battery, and I told you each of the individual resistors. Let's figure out what's the equivalent resistance for the entire circuit. Okay, so okay, so voltage source is here. So same as we've been doing all this week. I'm going to start on the opposite side of the circuit, which is A and B. Now these two guys, is that series or parallel? Parallel, parallel. I mean, these side by side waterfalls, same height, parallel. So can I do product over sum? Product over sum. Let's do that. So A and B are down here. Oh, now mine are 4 ohms and 4 ohms. Hey, if it took this guy 4 hours to paint a fence, this guy 4 hours to paint a fence, they make a 2-man team. How long is it going to take them? Take half the time of each individual one, so like 2 hours, right? That's always true. Whenever, guys, whenever you have 2 resistors in parallel that are each the same number of ohms, the overall resistance is half of either one. Okay? I can confirm that anyway. So resistance equivalent is 4 times 4 over 4 plus 4, 16 on 8. That is, in fact, 2 ohms. Okay, 2 ohms. Then redraw the circuit. Voltage, resistor E we haven't touched yet. So on my paper it says 6 ohms. Resistor D is 2 ohms. Resistor C is 2 ohms. And then A and B collectively is like a single 2 ohm resistor, right? Now it's 4 and 4 in parallel. That made 2. It's right there. Okay. Okay, so working back towards the voltage source. These 3 guys are all in what with each other? Series. So can I just add those up? Series. Okay. Then redraw the circuit. Okay, and last step. These 2 guys are in what with each other? Parallel. Right? Whatever current hits this junction, the current splits, gets pushed through both simultaneously. Yeah, that's a parallel setup. So the resistance total for the circuit is product over sum of those 2. 36 out of 12, like 3 ohms. 3 ohms. Or you could have said half of 6 is 3. 3 ohms equivalent for the entire circuit. All right, everybody good so far? Great. Again, you should have a nice number. It's probably an integer. I'd be like 1.5 or something. All right, voltage drop at each step. Ooh, actually, there's one we can get without really doing any math. Guys, what's the voltage drop across resistor E? Same as your battery, right? Okay, so for me, it's 12 volts. Can you just take the voltage from the battery and bam, copy paste that number right there? Right? 12 volts up, 12 volts down. That's the loop rule. Right? That's this one right here. Loop rule. Kirchhoff's loop rule. Okay. But now it's going to get a bit tricky. So what about the voltage drops across each one of these? Okay. Now, you know that these waterfalls have to add up to 12 volt, or well, mine would be 12 volts, right? Okay. But there's only 3 drops, but there's 4 waterfalls. But remember, these 2 are side by side, so you don't want to double count those. Okay. These 3 height changes have to add up to 12 units. Now here's where we actually have to go back to one of our middle steps. You guys remember this was one of the middle steps? Okay. There was the original circuit, and we combined these 2 in parallel, right? Then we went on from there. Okay? And this is where we can do this. Okay. So I'm going to look at this branch. So what? Now, not all the current is going to end up on this branch. Some of it goes through the tall waterfall, okay? But some of it goes that way. And whatever current does go on that branch, now I can break out this rule right here, which says that the voltage drop across each resistor is proportional to that resistor, right? Just like this one right here. Okay. Now all I have to do is throw in a third resistor in series, and then we'll go from there, right? Let's do that. So I know from this junction to this junction, there's a 12-volt difference, same as the battery. So the voltage drop across, what was this guy up here? That was resistor D. Okay. Voltage drop across D is resistor D over resistor D plus A and B in parallel, resistor A and B in parallel, plus resistor C. C, right? Yeah. All times the total voltage drop from junction to junction, which is the same as the battery in this case. So voltage drop across D is, I have 2 ohms here, 2 ohms over 2 plus 2 plus 2, and then 12 volts total. That's 2 out of 6 times 12 volts. It's like 4 volts. So my voltage drop across resistor D is 4 volts. Do the same thing for the other ones, right? So the voltage drop across A and B collectively, or A and B have to have the same voltage drop, even if they're different resistances. The same resistance, but that aside, right, they have to be the same height waterfalls. Right? If they are different resistors, all that means is that the larger resistor is going to be a little skinny waterfall with hardly any current, and the smaller resistor is going to be a big fat waterfall with a lot of current. Right? But they still have to be the same voltage drop. Right? So we can do this together. So collectively, that was 2 ohms. That comes from doing product over sum. So I'm looking at this guy right here. This guy right here. Out of 6 times 12 volts. Which for me, the numbers work out like this. 4 volts there. Now that's 2 resistors we just found the voltage for, the voltage drop, because they're side by side. So I can do A and B here, boom, boom. Okay. And finally, resistor C down here at the bottom. Okay. So this guy, so the voltage drop across C. Now that's a 2 ohm resistor, 6 ohms along that branch, 12 volt drop altogether. So this is how my numbers work out. Bada boom. Okay, working for you guys too. All right, let's finish the rest of the table real fast here. Joule's law. Power is current times voltage. Or sorry, Ohm's law. Current is voltage over resistance. So 12 over 6 is 2 amps. 4 over 2 is 2 amps. 4 over 2 is 2 amps. 4 over 4 is 1 amp. 4 over 4 is 1 amp. Okay. Across the battery, 12 volts on 3 ohms. That's 4 amps. Okay. Or if you follow it this way, I got 2 amps down here and then 2 amps from here. So those 2 plus those 2 combine to make the 4. Okay. Splits 1 and 1 in the middle. But okay. Power in watts. Now that's Joule's law. Power is current times voltage. So 2 amps times 12 volts, that's 24 watts. 2 amps times 4 volts, that's 8 watts. 2 times 4 is 8. 1 times 4 is 4. 1 times 4 is 4. Right? Just doing P equals IV all the way down. And last step. Right. 2 perspectives on this last cell. And if they both match, then you did everything right. So you could apply Joule's law at the point of the battery. So 4 amps, 12 volts, that's 48 watts. Does that, the other perspective is, does power supply match power demanded? So power demanded is 24 watts, 8 watts, 8 watts, 4 watts, and 4 watts. So I hope this adds up to 48. Boom, it does. There's 48 watts demanded, there's 48 watts supplied. Right, who's got any question? Any question? All right, when you finish that, as long as you have everything we've done in the last few days, then turn that into the grade tray. I'll grade that over the weekend. Into the grade tray. Let's wrap on the week.